Hello, and welcome to the lecture for Chapter 14 from OpenStax Astronomy. Here we're going to talk about, as the title says, cosmic samples and the origins of the solar system. These are two fairly separate ideas, but we can think of this as the loose ends, everything that we haven't talked about yet concerning the solar system, and of course with the details involving the sun yet to come. So cosmic samples, well, that's talking about asteroids, things that fall to Earth and are left over minerals, metals, rocks, and so on. Okay? Origins of the solar system are, well, what those samples come from. Because it turns out that a lot of the samples that fall to the surface of Earth are leftover remnants from the very beginning, the origin of the solar system. You can think of those samples as giving us a window into the solar system. Very indirect, very difficult to measure, but a small window into the very origins of the solar system. What do we compare that window with? Models, expectations, how we think a solar system like the one that we see today could have formed 4.5 billion years ago, because that's when it all started. Furthermore, we can compare our solar system, its formation, to the physics and behavior that we see in other solar systems. Because over the last few decades, scientists have been able to record the behavior of planets in thousands of other solar systems. We'll talk about data from hundreds of these solar systems that have been reviewed, but that data is coming in at a rapid pace today. It's very much the forefront of modern science. We can look at what other solar systems are like. Now, we can't get photographs of planets and other solar systems. They're simply too far away, too faint compared to the suns that they orbit, but we can still gain a huge amount of information about them through the way that they affect the behavior of the star that they orbit. But more on that later. Okay? Because of course we care about the origin of our own solar system, but we also care about how it fits into the whole. How does it compare to the rest of the billions of solar systems in our galaxy? So, when solar systems form, they form as a rotating disk of dust. All right? That dust is, well, composed of tiny particles that would qualify as under the word of dust, but also gas. So individual atomic gases and so on, molecular gases as well. This rotating disk all started from a nebula, from a big circular or amorphous spherical cloud. And we'll see that in an upcoming slide. But over time, if the conditions are right, that cloud collapses, it begins to rotate faster due to conservation of angular momentum, and it heats up due to conservation of energy. Now it's able to continue to collapse through a series of complicated processes that allow some energy to be released as light and gravity to do its magic, so to speak, by condensing matter further and further. Now most of the matter actually condenses right to the center. Some 99% of the matter condenses to the center, actually becoming the protostar, which then will eventually ignite, so to speak, into the star itself. And that's what actually we're going to be talking about in the next couple of chapters, is the amazing process of stars, and focusing on our own local sun to begin with. Now, here's the thing though, there's leftover dust, there's leftover gas, and that gas, also pulled together by gravity, starts to form these planetismals, primordial planets. All right, we can see them represented in this artist's rendition of a early solar system, a solar system in its formation. Excuse me. So as the solar system's forming, most of the matter coming into the star, eventually fusion starting in the star, we have planets forming. Now the planets haven't cleared out the gas yet. That's why we see these almost rings, right? These channels that the planets are forming. Furthermore, there are multiple planets per channel because the collisions between planetismals is ongoing in an early solar system. Okay? So there would be thousands of these planetismals in a typical solar system, or in models like our own solar system. We suspected that in the very early stage of our solar system, there were these thousands of small worlds, Pluto-sized worlds, moon-sized worlds, crashing into each other, but being pulled together by gravity. Okay? Some icy, some rocky. Okay? Now, we'll talk more about that primordial solar system, but let's focus on an interesting bit of scientific data that falls to the surface of Earth. Now, we pass through space debris all the time. Not leftover satellite type of space debris, but leftover comet trails, leftover remnants of the primordial solar system that are out there in the ecliptic disk that our planet Earth orbits through. And when that happens, when we pass through a particular cluster of space debris, we have that space debris contacting our planet, getting pulled in by gravity or just being in the way, and then as it comes into contact with our atmosphere, burning up due to the high velocity, relative velocity that this space debris had. That creates these meteor trails, these fireballs when they're particularly bright. Furthermore, when it's a big chunk of space debris, exactly like that left behind by a comet tail, excuse me, well, we approach this resting relative to the sun, more or less, this resting piece of space debris. Our planet comes in at a relative velocity. So imagine there's this big tail of space debris. Our planet is moving in its orbit with a translational velocity. And so we come crashing into it. All this leftover dust, very slowly moving dust. Yes, slowly spreading out from its own inertia, being affected by the forces of the solar wind and photon momentum conservation, but overall just resting in space. So when that happens, that causes a cyclical process of meteor showers. And so a lot of meteor showers, if you look at the calendar, you'll see that they happen every year on this approximately the same date. That's because Earth is going to pass through that leftover trail of space debris every year in Earth's orbit around the sun. And as we pass through it, the meteor shower appears to originate from one point, a radiant, in the same way that if you look down a long track of parallel rail lines, you'll see that they seem to emerge from a single point. It's just perspective, okay? And so then as Earth moves in, we have a meteor shower. So besides meteor showers being listed on particular dates of the year, they'll also be listed in a certain part of the sky where that central point is. You might look to a constellation, the meteor shower may be named after that constellation, and there appears to be meteors coming maybe every few minutes, or in the most extreme cases, every few seconds, streaks of light appearing in the sky. Those are the meteors, because the streak of light, particularly bright called a fireball, usually called a meteor, is the actual phenomenon. It's not the object itself, because when the object was in space, before it crashed into Earth's atmosphere, the object was dust, the object was a small asteroid, the object was a piece of a comet. So there's lots of names of what it was when it was in space, but once it starts burning up in the atmosphere and creates a streak, that is a meteor, okay? Now, meteor storms, as depicted here in this 1833 dramatic example, are when there's a meteor shower, but even more so. A meteor shower with thousands of meteors, one every couple seconds. That's a really possible dramatic event. And it can be completely harmless because it could be just lots of very small pieces, all burning up in the atmosphere, none reaching the ground, okay? So yes, it might create a minor warming effect if there's a lot of energy being produced, but overall, not a harmful effect, just a very beautiful one. Now, what's interesting is that meteor showers can lead to small pieces that make their way to the ground. Usually not, however, especially because meteor showers and their cyclic nature and just their abundance are associated with comet tails, because there's not enough leftover larger pieces of, say, metallic asteroids in the solar system at this stage of, this age of the solar system of 4.5 billion years. So when there is a lot of space debris, it's going to come from a comet tail. The comets being largely ice, because they come from part of the solar system where ice could form in large quantities. That, yes, some heavier minerals in there as well, some heavier elements, but large amounts of hydrogen-based ice, even water ice. Well, that ice is certainly not going to make its way to the surface. Even if it's a large piece of ice, it will burn up in the atmosphere. So meteor showers primarily burning up, very little reaching the ground. But other cases, there's other debris in the solar system, and that debris can be metallic. And the metallic cases can melt and have huge crevices from heat, but they can make their way all the way to the ground. This is an extreme example of a meteorite, okay, that was basically stolen by a farmer, put on display, now in a museum, known by humans long before Europeans came to North America, but really huge meteorite. Most meteorites are much smaller than this. This must have created a very large crater when it hit the Earth, a lot of energy released. Metallic, which is why it's so big. Some meteorites have some stony composition to them as well. We can see examples of that up here, sort of a more stony meteorite. A couple of metallic ones. This one is a composite of stony quartzy minerals as well as more metals, right? Now, what's interesting looking at these meteorites is that this is just what's left over from what was out in space, mostly burned up in the atmosphere, and then made its way to the ground. And then furthermore, collided with the ground, was further vaporized, but still some of these heavier elements left over. What's also interesting when we look at meteorites is that we can study them. We can see common traits between meteorites. They have particular elements in higher abundances than any rocks found on the surface of Earth, which really makes them stand apart from Earth rocks. So we can clearly identify them even in trace amounts. Even meteorite dust can be separated from terrestrial origin dust. And some meteorites come from pieces of asteroids, as we've talked about before. Other meteorites, even known asteroids like Vesta. Some meteorites even come from pieces of terrestrial planets. There are pieces of the surface of Mars that were thrown up into space from a large impact, achieved escape velocity from Mars, made it out into space through gravitational interactions, got pulled into Earth, and then crashed into Earth. Some of it left over. So now we have a meteorite that started off as a Mars rock. But even more interesting, perhaps, are meteorites that are considered primordial or primitive. So a primitive meteorite is one that is directly associated with, excuse me for spelling that incorrectly, meteor. Right, there we go. So primitive meteorites are those that have been around since the very beginning of the solar system. I was saying they're associated with the solar system, but there's more direct than that. These are actual pieces of rock and stone that never formed into those planetismals, never got caught up or differentiated in a planet, a dwarf planet or a full-size planet, never melted and reformed, but instead have been around in their original composition from the very beginning of the solar system. Some even dating from perhaps before the protoplanetary disk, before the nebula collapsed, because maybe they were left over from a previous solar system. In this process of galactic recycling that is on a scale much larger than individual solar systems like ours. So it tells scientists so much about what the story is of these heavy minerals existing in the first place in the universe, a universe that itself is some 15 billion years old, based on evidence of the Big Bang. So much we can look at these ancient rocks that come from space, left over, never formed into planets, primitive meteorites. And we can tell them apart from other types of meteorites, again, based on their composition, based on the elements that exist in them. One place scientists look for meteorites extensively is in Antarctica. The Arctic, less so, just because there's no landmass in the Arctic. There's kind of different. The ground is getting constantly churned up. The Arctic is essentially just all ice sheets floating on the water. But the Antarctic are huge ice sheets, positioned on top of land on an actual continent, and that's a place where you can really tell when a new rock has been introduced. Whereas if a meteorite ends up in the jungle, it'd be very hard to find. But it's much easier to find them, so the scientists can do surveys looking for the most likely place for them to show up in Antarctica. Okay, there are other places in the northern hemisphere they're likely to show up, such as Greenland and so on. So some terrestrial ice sheets as well. Here's an example of a meteorite going through the seat of a car. We can see this one is quite beautiful and kind of metallic, right? Very smooth, right? And as I mentioned, some other examples here. A, by the way, is carbonaceous, which is one of the types of asteroids. Remember, there was the C-type asteroids, M-type asteroids. Well, C-type asteroids were the carbonaceous type, right? This one has inclusions, so these little imperfections here, and this is something I was hinting at a minute ago, that may date back to before the formation of the solar nebula. So actually coming from some earlier process, from a previous star, right? The star that seeded the elements that made our solar system in the first place. All right, here is looking at another meteorite and its composition. Again, meteorites are the rocks, right? The rocks that came from outer space that didn't burn up completely. Okay, so we've hinted a lot about how meteorites are tied in with the formation of the solar system. So let's talk in more detail, more exact detail about the formation of the solar system. So a solar system like ours, in general, as a basic model, starts as a solar nebula, which is just a big cloud of gas. There's a cloud of gas on the scale of 10 light years or so for a star like ours, and it contracts. Why does it contract? Well, it contracts under gravitation. Any matter is attracted to other matter, so a cloud will naturally start to contract. Now, in certain cases, if there's not the right elements, that contraction can just slow down to practically a stop because there's a little bit of heat getting pushed back against gravity, and it creates an equilibrium of forces. Okay, so the heat pushes back, gravity pushes in, and the cloud is at a standstill. But in certain molecular clouds, as I mentioned before, energy is able to be released due to radiation, basically traveling away as photons or as light, and then gravity can continue to contract. In that case, as gravity continues to contract, the nebula shrinks and its motion causes it to flatten. Okay, so there's a statistical argument combined with a conservation of angular momentum that says a spherical cloud like this one becomes a disk like this as it contracts. And it also spins faster in the same way that as an ice skater pulls their arms in, they spin faster than when their arms were extended. Same idea here. As all this gas contracts, it absolutely has to spin faster. And the spin obviously increases quite a bit because we have a huge contraction. We have light years of distance becoming a 20th of a light year in distance. So huge amount of actual spatial contraction, volumetric contraction. So the nebula is a disk of matter, right? It has concentration near the center. So the huge amount of matter forming in the center, that's going to become the star, right? That takes some time. There's a long kind of stalling out process where that matter has to continue to contract depending on how much started in the first place and what type of star is being formed. But that's going to take tens of thousands to obviously tens of billions in the most hypothetical cases for the actual star to begin. But in the meantime, all the remnants of gas is spinning around in the disk, and then that starts to form as the protosun. That's, by the way, the name of the sun that hasn't started fusion yet, as that is in the middle. Then you have all the particles condensing, right, forming all those planetesimals. Okay, and we can see hundreds or thousands of planetesimals being formed. Now, what's interesting is this phase of a huge amount of planetesimal formation lasts for about 100 million years, okay? So 100 million years, in this, which is relatively short, okay, considering that is just a tenth of a billion years, or less than a 40th of the overall age of the solar system, because the solar system is 4.5 billion, or 40 sets of 100 million, right? So 4,000 million. Just 4.5 billion. But point being is for that first rather short amount of time in astronomical time, 100 million years, there would have been lots of planetesimals and lots of collisions. So no full planets being formed yet, because every planet that starts to be formed just collides with another forming planet. Okay, now this is interesting to think about, because if you recall when we discussed terrestrial planets and amounts of cratering, we talked about the era of heavy bombardment. Well, heavy bombardment lasted for the first 500 million years of the solar system. And that was a dramatic phase in itself, but that's once, say, Earth was already formed, being heavily bombarded, but already formed. Well, Earth could not have formed in the first 100 million because it would have just been torn apart. All right? So you kind of have these different really dramatic, chaotic early stages of the solar system. Okay? Now, what's interesting is the types of planets that formed in this planetesimal phase, and that formed and reformed and crashed into each other, but then eventually all the big pieces forming into one planet, depended on what type of condensations were possible. Chemical condensations, and this all has to do with distance from the sun and what is able to basically stay as a solid as opposed to a gas. Because a condensation is a phase change from a gas to at least a liquid, or in some cases in sublimation from a gas to a solid. Okay, so we see in the case of Mercury, we have metal oxides that are actually able to condense into solids. On any orbit with the sun of our energy output, on any orbit closer than that of Mercury's, metal oxides would not be condensed. Okay, so they would be in a phase of gas. So they couldn't then form solids because they're just going to bounce off of each other. You need to have condensation to then have amalgamation, gravitational attraction, and then bringing together planets. Okay, and I'll reiterate that idea in just a minute. We get out to the orbits of the other terrestrial planets, Venus, Earth, Mars. We see condensations of silicate minerals, which are abundant in Venus and Earth. And then in the case of Earth and Mars, we see condensations of iron oxides, olivines, different minerals that exist. Okay, they would be vaporized in the orbit of Mercury, so they're simply not found there. Okay, but what's interesting is then we get out past the asteroid belt, not to scale here in distance, but scaled with temperature. That's the ambient temperature because of the heat that's coming off of the sun. But as we get out to the orbits of, well, the gas giants, all cluster together here because there's not too much else that's being condensed, and also because the temperature isn't falling off as precipitously anymore. So that's why they're clustered. They're clustered based on this temperature scale here on the horizontal. But when we look at the gas giants, Jupiter, Saturn, Uranus, and Neptune, well, what's happening here is we have condensations, first of all and foremost, right at the orbit of Jupiter and its corresponding temperature, right? And that's the temperature of the space around it, okay? But anyway, we have H2O, so actual water ice. Then further out, right, we've got condensations of, and here as well, all right? Here it's containing H2O, but then H2O pure, then ammonia and methane, which are more associated with Uranus and Neptune. So what's so important there is that once you start to getting to a point of the solar system further enough away from the sun where the temperature is low enough, that's where water ice can form, and that's where you can get gas giants, because there's so much hydrogen, therefore there's so many hydrogen-based molecules like water, H2O, that there's a lot more of that to go around. These outer planets still have just as much of the heavier condensations, but proportionally they end up being tiny, right? So Jupiter, Saturn, Uranus, Neptune all have dense mineral and metal-rich cores, but they're surrounded by much larger, especially large compared to the terrestrial planets, outer levels of ice-based planet, all because those ices were able to condense because of the colder temperature, because of the further distance from the sun. So it's all about distance from the sun, about what planets can form, okay? The gas giants can only form at further distances from the sun, and that would apply to other stars as well. Okay, we'll come back to that idea in just a minute. All right, here's looking at the temperatures of Saturn. What's interesting here is we see that Saturn has different temperatures depending on the different gases, and furthermore, Saturn actually radiates quite a bit of heat due to continued differentiation and basically helium rain in Saturn. That heat wells up at the poles, interestingly, and we can see that showing up in the warmer color. Okay, and these different colors correspond to types of basically infrared or microwave radiation corresponding to low temperatures and the different wavelengths of those lights, and then color-coded so far in the image. Okay, so as I said before, understanding our solar system, the origins of the solar system, basing it off of direct data from meteorites, thinking about the models that make the most sense, well, that's all great, but it needs something else, and modern science has that something else, and that's comparing our solar system to other solar systems. Because we can look at other solar systems nearby in our arm of our home galaxy, the Milky Way, and we can see solar systems that are in different stages of formation, essentially different ages. We can see early solar systems that are still in the disk phase. We can see fully developed solar systems, and then we can think about the trends. Now, this is an example of a solar system that is in the protoplanetary disk phase. Notice it doesn't look like much. It just kind of looks like this weird blurry rectangle. But that's because we're seeing the dust. The dust of a protoplanetary disk would be so dense that it wouldn't let any light through, any visible light. So when we look here, this black region isn't the absence of something. It actually shows the dust, okay? Shows it as a clear disk, right? Much shorter on one axis than the other, right? So it is disc-shaped. Okay, blurry but disc-shaped, right? This other image shows the clear light coming up of the central protostar, and again, the disk of that protoplanetary system, okay? What's amazing is that this is actually also an image. This one isn't taken with visible light, but instead is composed from radio waves. So sort of shorter wavelength, something kind of around microwaves, but a little bit longer than microwaves, but well classified in the radio wave spectrum of EM, EM radiation. And we can then bring together a resolution that's actually comparable to the resolutions we get with actual visible light telescopes. And that's all thanks to big projects like the Atacama Large Millimeter Submillimeter Array, right? Which we talked about way back in our chapter on telescopes. But the point is that this clearly shows the bands of these protoplanets, these early planets, these planetesimals that are forming and clearing out the gas as they gravitationally attract in the gas. Now, what's interesting is what happens to the gas that kind of between the bands, the stuff that seems like it's just going to linger, right? Because we don't see that in our solar system. Well, that can continue to get blown away from the solar wind that's being produced from the star, and that gets produced at different rates depending on the age of the star, and eventually will get gravitationally pulled in very slowly over time to fully formed planets. Here's an artist's rendition of the same process, right? Showing that the gas that gets left over doesn't just form kind of gaps, but actually forms spirals. An interesting idea for a strange type of planet that we see in abundance in other solar systems. I'll talk about that in just a minute. Okay, right? And that minute has passed because we're going to now talk about two types of planets that we see in the other solar systems we've surveyed. Okay, so first of all, let's take a minute and appreciate that these are transiting planets around other stars. These are the number of planets that scientists have measured. All right, here are their masses compared to the mass of Earth. So notice that these are hundreds of planets that have been counted. For example, there are planets in the range of 1.9 to 3.1 Earth masses that scientists have counted around other stars that count up somewhere in the 800 to 1,000 range. Now this is data that's back from 2016. So now there's probably many, many more that have been counted. Okay, this process is getting automated quite a bit because there's just so many solar systems for scientists to look at. But again, how do scientists actually count planets around other stars? I mean, their distances are so great and the light is so faint. Well, they actually look at the transit because they measure, among other things, the wobble of the star, because they can get a very accurate measurement of the Doppler effect, which is this slight change in the wavelength of light produced from known elements of known types of stars. Seeing slight changes in that wavelength of light tells us the velocity of the star. Why is the velocity of the star oscillating back and forth? Because the star is wobbling. Why is the star wobbling? Due to gravitational interaction with the planet that's orbiting it. Especially large planets cause a significant amount of wobble in their star. For example, Jupiter causes our sun to wobble quite a bit, right? A very measurable amount of wobble from, say, that an alien could measure in another solar system. What's interesting is there's other methods as well. Scientists can actually look at variations in the intensity of the light as the star is partially eclipsed as the planet passes in front. All right, so there's other ways, and it's quite remarkable. There's even some direct images that have been taken of these planets around other stars, which are called exoplanets. Exo because they're out of our solar system. All right, so this is a survey of exoplanets in this figure shown here. And notice right away that there are quite a few planets that fall into a category that's bigger than Earth, but smaller than Neptune. And not just quite a few, most of the measured planets. My goodness, what's going on there? Well, that's because there is a category of planet that apparently is common in other solar systems, the thousands that have been surveyed, that we simply don't have. A super-Earth. Super-Earth. Why called a super-Earth? Because these planets are either small gas planets or terrestrial planets, and they appear to be both based on the actual, basically the types of elements that we can measure being reflected off these planets, which is a testament to how good these measurements are getting with exoplanets. But these super-Earths are somewhere in comparison of size between Earth and Neptune, right? Quite common in other solar systems. Right? Masses of 1.9 to 3.1 Earths, for example, or even 1.2 to 1.9 Earths. And then once you get up to the size of Neptune, because Neptune is about 4 times larger than Earth in mass. Okay, that would just be a Neptune-like planet, which we've also measured. All right, we've measured some planets that are actually Earth or Venus size. Okay, but we've also measured quite a few planets that are larger. A lot of Jupiter-sized planets or Saturn-sized planets. Okay, but again, mostly super-Earths. Okay. Also interesting, when we look at the planets that are being discovered, we see there's a trend. So early, the first planets that were discovered back around 1990 and then throughout the 90s up to about 2000, and not so many at first, right? The amount that have been discovered recently greatly outnumber those that are measured earlier because the methods are getting better, getting refined. But there's also been a real trend in the size, because at first only the biggest planets could be measured, because the techniques were only sensitive enough to measure the biggest effects, which came from the biggest planets, the most gravity, right? So at first it was all, bigger than Jupiter, mostly sized planets that were being discovered, okay? Now we're able to discover planets that are right down to Earth size. Okay, so smaller planets, quite a few super Earths. So perhaps we're seeing more super Earths because they're easier to measure than Earths, or certainly much easier than Mercury-sized planets. Good luck measuring something that has that small of effect on a star. So there is a selection bias there. There is the fact that it's easier to measure large planets, so we're going to see more of those, which just means we just have to continue to refine our methods and collect more data and see how the trends work out. But even if super Earths aren't more common than Earths, they certainly exist. Okay, so it's a type of planet that we simply don't have in our solar system that is at least out there in the overall population of solar systems. Furthermore, there's a lot of these big Jupiter-sized planets, a lot, right? So big gas planets seem to be very common. But here's the remarkable thing. Not all of these gas giants are as far away as Jupiter. Some of the gas giants, so we can say some giants, are close to their star. Close to their star. So what's the significance of that? Well, that tells us that that's a whole different category of planet. That's a Jupiter that has an orbit, in the case of these first measured ones, an orbit that is as close as Mercury. So we have a Jupiter-sized planet that's really close to its star. These are called hot Jupiters. And this has been a very common type of planet that's been discovered, almost certainly because of this selection bias, right? So this selection bias of planets, selection bias, because hot Jupiters would be really easy to measure. It's a large planet with a lot of gravitational pull. It's close to the star that it orbits, so that means it's going to be pulling on it more than if it was as far away as Jupiter is from the sun, and Jupiter already pulls on the sun a significant amount. And it has an orbit that only takes a few days, so that cyclic process would be easy for scientists to recognize. If you're looking at an orbit that takes many years, good luck actually, picking up that signal, because you have to see it change. So, scientists have to be very patient with their observations. So, right, it's a type of planet we're going to be able to see. But again, it's a strange type of planet, because as we talked about before, we need condensation for gas giants to form, which means that these gas giants have to form far away from stars. So when we look at hot Jupiters, large gas giants that are very close to their star, that means that the planet must have moved. And I know that sounds pretty fanciful, but that is the best hypothesis that scientists have. That's the best working theory. Jupiter-sized planets form outside, and on the edges of the solar system, or at least far enough away from their stars, so that H2O and other hydrogen-based molecules are able to condense. But then, due to interaction with the protoplanetary disk, they're actually pulled inwards. And scientists have plausible models that suggest how there would be a gradual force pulling the planet inwards, essentially spiraling it in until it stabilizes in a very close orbit. But then that begs the question, why did that not happen in our solar system? Well, there's some suggestions that our star, it has a particularly, a category of star that was particularly active in terms of its ion wind, its solar wind, and blew away dust, the same dust that would allow, say Jupiter or Saturn to drift inwards, so that, that process never happened. And there certainly would be other solar systems like ours that don't have hot Jupiters, but then maybe there are, half the population that do. Okay, so a lot of interesting continuing research trying to understand how unusual our solar system is, or how usual our solar system is, or what makes our solar system slightly special or very special, or so on. Because it's all wonderful speculation, especially in the context of the fact that our solar system harbors life, the only life that we know of in the entire universe. Okay, so one thing we want to touch on now as we wrap up our discussion for this chapter and the formation of solar systems is some ideas that actually would have been well suited back in the chapter where we talked about terrestrial planets in general, just about kind of the rules of how terrestrial planets can form. Because we talked about the condensation and how, only gas giants can form far away and they must drift inward to become hot Jupiters. But there's also variation within the terrestrial planets, so terrestrial. So some, basically cool very quickly. So if you look at a planet like the size of Mercury, or a world like the size of our moon, well, that planet was small enough and it had a small enough surface to volume ratio that it was able to cool completely and have no activity left. Whereas something Mars-sized is going to have reduced volcanism and basically mantle solidification. So no tectonic activity for something like Mars. Whereas for Venus and Earth, we're going to have basically reduced volcanism compared to an even bigger planet, say a super Earth, and some plate tectonics, right? In Earth's case, definitely continued plate tectonics, but Venus is perhaps having fully stopped. But if you had a bigger planet, they're at this stage, basically a solar system of our age of 4.5 billion years, right? Well, then you might have a planet that is still in the widespread volcanism phase, even after that point, because it's so much bigger, it's going to be cooling more slowly. Also, if we took a snapshot in time early in our solar system, we would see all these planets earlier in their stage. The point is that smaller planets advance through these stages more quickly. Larger planets advance through the stages more slowly. Okay? Furthermore, larger planets have greater gravity, which means that features like large volcanoes collapse under their own weight. Smaller planets, Mars-sized planets, because Mars is significantly smaller than Earth, right? We have possibility of very large mountains forming. And we can see that idea hold up, that theory hold up in our own solar system, because by far the biggest volcano in the solar system is on Mars. And you can see its dramatic comparison, Olympus Mons compared to Mount Everest, or even Mauna Loa, mispronounced it there, but Mauna Loa, or the Maxwell Mountains, which I believe are on Venus. The Maxwell Mountains on Venus, yes. All right. So by far, Olympus Mons way, way bigger, huge, unbelievably large volcano, but possible to exist because of the significantly less gravity. Mars has about 1/3 the gravitational acceleration of Earth, a lot less force pulling that mountain down, so it doesn't collapse under its own weight. Here's a overview composite image of Olympus Mons. Dramatic terrestrial phenomenon explained by the general principles of planet formation. All right. Furthermore, this idea holds that smaller asteroids have irregular shapes because gravity never pulled them into a spherical shape, right? Spherical shapes start at a certain size for terrestrial planets. They start at slightly smaller size from our ice-based worlds. So you have smaller spherical ice-based worlds because ice has a lower basically stress level, lower strength level. So gravity is able to collapse it and form it into a sphere. But in this case, gravity never did that with these irregular shaped asteroids, so they remain irregularly shaped. And that concludes our lecture on basically meteorites, the samples that fall to the surface of Earth from outer space, primitive or otherwise, and how that ties in with a whole discussion of the origins of solar systems, ours in particular, and in comparison to all the data we have about exoplanets and other solar systems. I hope this lecture has been interesting and informative. Thank you so much for watching.